before diving into the details of methods for finding our y sub p, these particular functions, it's going to be helpful to have an idea of how differential equations can be viewed in a different light, right? I mean, right now we just see these as equations and they happen to have derivatives in them, and we are trying to essentially figure out what could possibly be the solution. But there's actually another way of looking at these differential equations that will actually shed some light on the method that we will use to find these particular functions. So let's say we have, and I won't be too abstract here. Let's say I have something like this. And so, and let's make it non-homogeneous. So let's say we have x squared minus 3x plus 1 right there, right? And this is our differential equation. So we can see the left-hand side is something that's familiar, right? And we know how to solve it if we have a 0 on the right-hand side. But the interesting thing is, if I take this entire expression here, and if I just call it something like, like L of y, because when you think of what's going on at this side, the operations here are with respect to a certain function. So it's like you're trying to find a function that when you differentiate it twice and subtract 2 times the first derivative and minus 3 times the function, it's going to give you this quadratic. So it's almost like on the left-hand side, there are a set of operations that are being performed on a specific function, and you want to know what that function would have to be, right, in order to produce this output. So it's almost like you have a input-output problem, right? Where I'm just going to label this like L of y. And, for this particular function, or anyone in for that matter, when I plug a certain thing into the left-hand side, I will get a certain output, right? So for instance, as an example, suppose I wanted to find L of like e to the x, right? So suppose I were to put e to the x into my magic function here, my magic box that happens to be the left-hand side of this differential equation. Well, what would it do? It would take the second derivative of the e to the x and then minus 2 times the first derivative of e to the x minus 3 times e to the x. And then what would the output be? Well, the output would be, I differentiate e to the x twice, I'll still get e to the x. And then I'll have minus 2 times e to the x minus 3 e to the x for negative 4, right? E to the x. What would happen if I plugged, let's say, a sine function in here? Let's say the sine of 2x, for that matter. Let's say we did that. Well, what would it do? Well, again, it would do what it does. It will take the second derivative of the sine function minus 2 times the first derivative of the sine function, the sine of 2x, and then minus 3 times the sine of 2x. And again, it will give me some output, right? Now, clearly, when I plug an exponential function in to my special function, it gives me another exponential out. If I plug this trig function in, well, if we want to see the details, well, when I differentiate sine of 2x twice, and you can verify, you're going to get negative 4 sine of 2x right? Because if you differentiate it once, you'll get 2 cosine of 2x. Differentiate it a second time, you'll get your negative 4 sine of 2x. When I differentiate it once and then multiply by negative 2, I will have a negative 4 cosine of 2x. And then here, I will just have my minus 3 sine of 2x. So the output here, interestingly enough, is actually a linear combination of sine of 2x and cosine of 2x. So what is that specific one? So it's negative 7 sine of 2x, and I'll write it minus 4 cosine of 2x, right? So there we go. So again, going back to my original problem, clearly, if I am trying to find what, in trying to find what type of function could I plug into this left-hand side in order to get a polynomial like this, clearly I couldn't plug something like e to the x in and hope to get a polynomial out. It wouldn't work. Also, I couldn't plug like a sine or cosine function in because, again, even if I did cosine of 2x, the operation would be very, very similar. There's no way I would get a second degree polynomial out. But maybe, so again, we're just illustrating here. What if we plugged in something like, so let's pick a really random quadratic. So let's say I did negative 1/3 x squared, let's say plus 13 over 9x, and then minus 41 over 27. So let's say we did that. Well, again, what would it do? It will take the second derivative of this is 1/3 x squared. So it's going to take the second derivative of this. All right, so double prime, and then it's going to take minus 2 times the first derivative, again, of the same function that we're plugging in. And then it's going to take minus 3 times that function, the negative 1/3 x squared plus 13 over 9x minus 41 over 27. So let's see if we can simplify this. Well, if we, and I'll just to help, I'll write the first derivative over here. Well, in fact, what we can do, we don't have to write it on the side. Let's do the first derivative first. So this should be a minus. So minus 2. When I differentiate this once, I'm going to get negative 2/3 x plus 13 over 9. And then, of course, my constant goes away. Let me bring down this one. And now that I know what the first derivative is, I can find the second derivative and then put it in front right there. So we have plus 13 over 9x minus 41 over 27. So when I differentiate again, I'm just going to be left with a negative 2/3. There we go. So let's simplify this and see what we get. So we have negative 2/3. If I distribute the negative 2, I'll have a plus 4/3 x, and then a minus 26 over 9. And then distribute the negative 3. What do we end up with? I have an x squared, so a plus x squared. And then for the x term, I will have, what's that? Negative 13 over 3. So negative 13 over 3 x. And then for the constant term, we'll have a plus, and what's that? A 41 over 9, right? And then let's see, what do we have? So so we have an x squared term. So we have that. So that's x squared. For an x term, I have 4 minus 13, so that's negative 9 over 3, so that's negative 3x. And then what do we have for the constant term? Well, this I can write as negative 6 over 9. So negative 6 minus 26, so that's negative 32, plus 41, that's 9 over 9, that's 1. And let me see, is that what we want? Yep, there it is, x squared minus 3x plus 1. So it seems like this would be the specific quadratic that when I plug it into my special function that's based on the differential equation, it gives me the exact output that I want, right? So the question is, and one of the fundamental skills that we're going to have to utilize when we have to actually go through and solve these is based on the type of output that we want, right? And that's going to be dependent on the differential equation, the non-homogeneous differential equation. Depending on the type of output that we want, can we determine what the input would have to be, right? And that's basically the idea behind one of the methods of finding the y sub p. Based on what the differential equation is saying should be the output, what input should it be? And then we'll have a specific way of coming up, how did I know it was negative 1/3 x squared plus 13 over 9 x minus 41 over 27? And no, I do not have a crystal ball. I wish I had a mathematical crystal ball, but no, there is a process that we can use to figure out what these coefficients are. As long as we know what type of function it should be, then we can figure out what the coefficients would have to be. So it could, in this case, the specific, or the y sub p, could not be an exponential function. It could not be a basic trig function. It would have to be a quadratic of a certain degree, right? Now, so, the title of the video is Differential Operator, and basically that's what it is. That so the left-hand side, of our linear DE, so of the DE, may be viewed as what we call a differential operator. Operator in the sense that it does something, but in this case, the thing that it does involves derivatives. So we call it a differential operator. And again, the goal is, right, so the goal is to determine what input, right, of this operator. So what input of this operator produces the required output, right? And sometimes you might have to use some, almost like an educated guess and some ingenuity. Other times you might have a specific formula that tells you what the input has to be. Now, one last thing I just want to say, I'm gonna write down the differential equation again instead of having to scroll back up. But what I'm gonna do now is to wrap this up. Suppose it wasn't non-homogeneous anymore. Suppose it was 0, right? Well, again, what would our problem entail? So again, if I call this my L of y, and I'm just choosing a letter L that we haven't used just yet. I don't want to conflict with anything. So here is my differential operator, and again, from this standpoint or this perspective, we now would like to know what the input would have to be in order to produce a 0, right? So, in the light of some of the theory from linear algebra, when we're solving a homogeneous, in fact, let me just say it, when we're solving a whole D, what we're actually finding is the kernel of this differential operator. Isn't that really interesting? Because remember, the kernel of one of those linear transformations, right? Or they're sometimes called linear operators, right? That would be the set of all inputs, right? That get mapped onto the 0, in this case, 0 function, right? So when solving, when solving a whole D, right, we are actually finding remember there were two names that we gave it, the kernel, come on, that's one L, or the null space. So the kernel or the null space of our differential operator. So of the differential operator. And we have a method for that. In fact, for this one, and you can verify, you can go through, set up the auxiliary equation or the characteristic equation, find the roots, and determine which of your three cases. But I'll just say, note, the kernel in this case, the kernel is, and I'll write it down, so it's a set of all functions of this form. It turns out that this is a case 1. It's really simple, but it's C1 e to the negative x plus C2 e to the 3x, where of course your C1 and your C2 can be any real number. So what this says is anytime I put any function of this form, so in other words, any scalar multiple of e to the negative x plus a scalar multiple of e to the 3x into my differential operator here, I'm always going to get an output of 0. So all these functions are mapped onto the 0 function, right? And there you go. So I just wanted to kind of, give you a very different perspective, a different way of looking at differential equations. And it's not just, okay, an equation and you manipulate it, but you can literally think of it as a function or an operator or a transformation that takes a certain input. And in this case, our input is a set of functions, right? And it produces a certain output. If that output is 0, then you're essentially working with the kernel. If the output is not 0, then you're looking at a specific element in the codomain, and you want to figure out what element from the domain would get mapped onto that specific one, right? And so now that you have that notion or perspective of a differential equation, I think it will make our method, when we actually go through and learn how to find the specific inputs for different types of outputs, it will make if you keep this idea in mind, it will make that process a lot more easy to understand. All right, well, let's test that theory and jump into the methods right now. See you then.